All right. Do you think we can start now?
Yeah, sure. So, same plan as yesterday, guys. We'll be doing the polls because everyone loved those a lot. Then we'll be going over some homework solutions briefly before we actually go into today's topic, which is combinatorics and competitions. So, Akash, if you want to start off with the polls.
Yeah. All right.
Hopefully, a lot of you have watched. Okay, I'm already seeing some questions about what is Avatar.
So this is a reference to the show Avatar: The Last Airbender.
Which some of you may recognize from my background here. And this is from one of my favorite episodes. If you haven't watched it yet, I would definitely recommend it. It's on Netflix. Avatar: The Last Airbender. It's a great show. Obviously, I think most of you know what Star Wars is. Sport, of course. Hopefully, you all have watched Shark Tank as well. It's a show that I used to watch a lot when I was younger. Okay, a lot of you are asking what it is. Basically, it's kind of like an investment pitch show. So, it's just a series of people who are interested in marketing their product or business to a bunch of these millionaire or billionaire investors, right? So our question 4 is just a list of the investors that have appeared on the show, like, Mark Cuban, who's the owner of the Dallas Mavericks, Barbara Corcoran, who ran a real estate company. So, like, if you haven't watched the show, it's going to be hard for you, but I think if you have watched the show, it's a pretty interesting question.
All right. Almost all of you voted, so we'll just wait around another minute and then see the results. All right. So it looks like almost all of you voted, so I will share the results now. So for favorite character, we got Cabbage Guy. Wow. It's somewhat of a shocker, but understandable. Especially if you haven't watched the show, I would probably select the name Cabbage Guy. So that might be why it won.
I see we have
Star Wars character, R2-D2.
We have Qatar next for Avatar. Great. Looks like we have Zuko and Iroh, surprisingly low at 8%. Usually Iroh is the most, actually. Star Wars.
Sport to watch. You have basketball, some soccer.
Darth Vader.
Mark Cuban, that's a very common choice. I would agree.
For sure.
He just knows what he's doing. Dogs versus cats. Dogs. I respect it. I would like to get a dog. Although people in the household object. We got some complaints about why was there no both option. Yeah, we should have put both. So as you can see, we have Austin here with us. He's one of our panelists, and he's an avid swimmer. So he's pretty psyched that we got a decent amount of votes for swim. All right. Let's see. I think the results are pretty expected. All right. So I guess to begin, we can go over some of the homework questions you had. So I'll just put that up real quick and we can discuss them. All right. All right, so can you see the inequalities?
Gosh, I think it's good.
Oh, of course.
No, it's not.
All right. So I never know if I'm sharing the right thing. Anyway, so I'll just make this presentation mode. So I believe these went pretty well for you guys. Just to offer a hint in case it didn't, we'll get through some of the feedback forms that we've gotten with specific questions. But just to give a general outline to push you in the right direction, in case you want to think about it a little bit more, here I would definitely advise one, not dealing with the denominator at first. So there's going to be a dividing by ABC step towards the end. And I would also definitely think about AMGM. And just as a hint, you're actually going to have to apply AMGM twice. So I know that the other problems, they're more introductory. So you basically just had an expression and you just have to apply AMGM once. So this is definitely a harder problem. So you have to be a little bit smart about what sequences you choose, and then you're actually going to have to apply AMGM 2 times to finally get what you want. And then we can also talk about this problem. So before I give anything away for this one, I just want to see if I can launch a quick poll about it. So there should be a poll launched. So when you see this inequality, we're just curious, which one does it make you think of? Of the 4 that we covered yesterday, AMGM, Cauchy-Schwarz, T2's lemma, and Nesbit's inequality, there's one that it's actually pretty similar to. Around half of you voted, so let's wait another 30, 60 seconds.
All right, Akash, what's the poll looking like?
All right. So share. So a good amount of you see the resemblance to Nesbit's inequality, which is correct. I can understand AMGM because we've talked a lot about AMGM. It's definitely one of the most useful inequalities you'll ever learn, and used a lot to prove other inequalities, which is really cool. But yeah, this one definitely is like Nesbit's inequality. So if we just remember what Nesbit's is, we can just write it up real quick.
Yeah, Akash, you can also go to the previous slides. I think Nesbit's is written down somewhere.
All right. All right, so I'll just scroll back. So this is what Nesbit's inequality stated. So just try to remember this. You basically have 3 numbers. You kind of put them in this fraction form. You put all 3 numbers on the top. And then the denominator is basically the sum of things that are not in the numerator.
Yep.
So then if we go to what you guys thought about for homework, it's actually very, very similar. You have 4 numbers now instead of 3. The 4 numbers, as just like in the 3 case, they're all in the numerator, and the denominator is the sum of what you don't have. And then we're saying now is greater than or equal to 4/3. So a hint here would be definitely go back to Nesbit's inequality. And while you can't directly use Nesbit's inequality, like, for example, the other problem the hint was to use AMGM, what's useful in this problem is to think about the proof of Nesbit. So I know we went through that rather quickly yesterday, but feel free to go on the YouTube or the slides to check out what the proof of Nesbit's is. And then you should be able to replicate it for this problem. It's actually very, very, very similar, just 4 variables instead of 3. And then for this last problem, I know it looks very complicated and looks very weird, but it actually is the same thing as Nesbit's in the previous problem, except instead of 3 or 4 variables, now you have n variables. So just to describe what's going on, because maybe sigma notation might be a little new to some of you, essentially what you have here is that you're summing a bunch of fractions, and what you have in the numerator is all your numbers, right? Each x. So if we go back to the previous example, it's just like this, right? This would be x1, x2, x3, and x4. And then the denominator is first you sum all the x's, and then you subtract xi. So another way of thinking about it is just that it's the sum of all your numbers except for what's in the numerator, which again, I'll go back to the previous slide, that's exactly what we had here, right? The denominator is the sum of what's not in the numerator. So you have to take a, b, and c, and d. This one has the a up top, so you don't include it down here. This one has the c up top, so you don't include it down here. So it's the same logic here, and then you can see there's this pattern of n and n minus 1. So for the 3 case, it was 3/2. For the 4 case, it was 4/3. And in this case, it's going to be n over n minus 1. So this is definitely on the more difficult side, just because of all the variables floating around. And especially there's not like there's not very tangible numbers to deal with. But again, if you're feeling ambitious, really try to think about why the Nesbit's proof work, and then you should be able to figure this one out.
Yeah, gosh, I think one thing in general that you guys should notice is that like here we were essentially like by providing Nesbit's and like the homework problems, we're essentially working up to like this generalized solution. And I think just like in general, like a thing to keep in mind when doing like math is you should really always like if you can like think about how certain properties of like functions, numbers, anything you're dealing with, any patterns you see, how they can be generalized in this form. And I think that'll be really important whether you're considering going into math or not. But I know like a lot of research is really involves it involves like really working with generalizing some of like the findings you find and just generalizing the patterns you see. So I would just always try and keep that in mind. If you think that something can be generalized, perhaps try and think about it, do a quick Google search about what other people are thinking and see if you can understand that answer as well.
Yeah. So I'm just gonna scan the Q&A real quick just to see if there are any questions about this. Foyez, just let me know if you see anything.
I think we're good. We're good to go.
All right.
So today's topic for everyone is we're essentially looking at combinatorics in high school math competitions. So that ranges just from like a variety of math competitions, and we've put together a collection of problems that we'll be solving today. So it would be helpful if you have a piece of paper and pencil. And since today is math club day, we decided to perhaps do a little fun activity while we do this. At the same time, we decided we would play a little bit of math bingo, and I can explain how it works. So we would like you guys to like create a 5x5 like grid, like a bingo board, a 5x5 bingo board, and put free in the middle. So the middle square will be your free square, and essentially we want you to fill out the rest of the 24 squares with any numbers between 1 and 40. and essentially as we go through the problems, a problem will be associated with a number, which will be at the top. And if you have that number on your bingo board, just cross it out. And we'll see if someone gets bingo. I think just the fact that you guys are creating your own bingo boards and like the fact that you have to choose numbers between 1 and 40, it might be very unlikely that many people get a bingo, but we'll see. We have a lot of people joining us, so perhaps there might be a bingo.
All right. So as Foyez said, we're going to be doing some combinatorics today, and specifically within competitions. And then just a quick description of what Foyez said, just the bingo rules. So we have a 5x5 grid, and then Foyez, I forgot to mention here, but just remember to give yourself the middle square free. And then fill it, I guess, with 24, not 25. Pause integers from 1 to 40. And then each problem is going to have a bingo number. So it'll be a random number between 1 and 40. And if we review a problem that is something that you chose for your board, then cross it off. And then the goal is to get 5 in a row or column.
Yeah. Also, I think if you get it in a main diagonal, maybe that might work.
Yeah, main diagonal as well.
Main diagonal, so the 5 diagonal.
All right. So I guess we can go on to the first problem. So a lot of these are, so this one's from the AMC. It's a fairly well-known competition, which maybe many of you have participated in. So I'll just read out the problem, and then we can think about it for a little bit. And then, of course, we'll discuss how to do it. So we have a dessert chef prepares the dessert for every day of the week, starting with Sunday. The dessert each day is either cake, pie, ice cream, or pudding. The same dessert may not be served 2 days in a row. And there must be cake on Friday because of a birthday. How many different dessert menus for the week are possible?
Yeah, and so notice here that this is not really related to the problem, but this problem is associated with the number 12, as you see at the top. So if you have a 12 on your bingo board, just cross it out. Yeah. Okay. So there's still a lot of people saying that they're still making their bingo board. Yeah, you guys can take this time to make the bingo board, and if you want, like, put the 12 in, you'll get a free square. Yeah, and we'll give you some more time for this problem.
Oh, just a clarifying question, which is probably pretty important. It says someone asked you to cross off the number 8. So this is just really us just sourcing the problem, because especially if you're taking it from competition math is the theme today. So you just want to let you know where we're getting these from. But the number you see up top in parentheses, so you see the 12, that's what's the bingo number, so to speak. So don't cross off if you have an 8, cross off if you have 12. And as I said, we understand that we did not give enough time for the board, so feel free to put a 12 on the board if you're still making it.
So it seems like in the chat we have Q&A. We have a question: does the chef serve dessert on Sunday? Yes, he does. He serves dessert on every day of the week.
All right, some people are beginning to put some answers in the chat, so we'll just wait a very short amount of time, 30 seconds or something, and then we can start to go over. All right, so I think we can start to go over. So let's go to solution. So it looks very long, but the idea is actually pretty simple. So first off, again, remember the problem said that you cannot have the same dessert 2 days in a row. So on Friday, there's just that one possibility. You have to have cake. Someone has a birthday. So there's just one possibility. Then going forward to the next day, you have 3 possibilities. Basically just everything except what you had on Friday, right? The cake. So you can have the pie, the ice cream, or the pudding. So that leaves you with 3 possibilities. Then you start going backwards. So this is actually a key idea. So going backwards instead of forwards allows you to think about more clearly as to how many possibilities you have. And then you can kind of go along the stream of logic to see that you actually have 3 possibilities every single day. So we can just go through a few examples. So on Thursday, you have 3 possibilities, the pie, ice cream, or pudding, because you couldn't have the cake because cake is the next day on Friday. Then you have the same thing on Wednesday. You have 3 possibilities. And essentially the 3 possibilities are the 4 desserts except for what was had on Thursday. And you can actually keep repeating this process and then apply it to Tuesday as well as Monday. And then as you know, the solution in Sunday, you might think that there are 4 possibilities, but actually there are only 3 because of what we have on Friday ends up limiting what we can have on Sunday. So that means that the number of possible menus is just you multiply all the possibilities for each day. So Friday, remember, that represents this 1 we see over here, but every single other day was 3, essentially stemming from that logic that you cannot have the same dessert 2 days in a row. So then you just get 3 to the 6th power, which is 729. All right, I think a lot of you put 729 in the chat, so that's really cool. Just gonna check the chat Q&A just in case there are any further questions. Yeah, there's a chat that says, "Oh, rip." Yeah, definitely. It's easier than you might think. Sometimes it really is just what you think it is.
Yeah, I think a key to this problem, like if you also look up on the annotation at the top, so like a key thing is you really just wanna choose a set day that you want to work around. And so since Friday we're restricted to 1, to essentially 1 possibility for dessert, it seems logical to work around Friday, and then we can determine like essentially how many possibilities we have by just essentially using Friday as kind of like our fixed point.
All right, so I think we can move on to the next one.
Yeah.
Just gonna clear the annotations. All right, so let's read it out and then we can think about it. So a player pays $5 to play a game, and then they roll a die. And then if the number on the die is odd, then they lose. And if the number on the die is even, then you get to roll the die again. And then if this is the case, then the player wins if the second number matches the first, and otherwise he loses. So how much should the player win if the game is fair? So here it gives a description. In a fair game, the probability of winning times the amount won is what the player should pay. So this is something related to the idea of expected value, if you've heard that term before. That idea of probability times the value that comes from that case. But here they just give you a definition that's pretty simple to think about. So if you're not comfortable with expected value or don't know what that term means, you should be fine.
Another way you guys can think about it is that the probability that you win should be proportional to the amount you pay. And so in some sense, if you'd like to think about it in a more like economic or game theoretic like approach, you could think about it as like you're basically compensated for like the amount of risk you put in if you win. So your risk and potential compensation is proportional.
By the way, just because I don't think we mentioned it before, and just to reiterate what we were talking about in terms of bingo. So if you have an 8 on your board, you should be crossing that off just because there's an 8 there. So that's the bingo number. So if you have an 8 on your board, feel free to cross that out.
Do you think we should move into the solution now?
Yeah. Right. So first off, we compute the probability that the player gets to keep on playing. That is, they don't lose on just the first move. So the probability that they don't lose on the very first turn is half, right? Because they need to roll an even number, and the probability of getting an even number is half. And then if you want to get the same number on the next turn, then the probability of that is a sixth. Because for any number you roll, if you want to get the same exact number, there's only one number out of the 6 possible numbers on a die that will give you what you want. So that's a sixth. So that means that the probability that the player wins is a 12th. And the goal here was for the game to be fair. So in other words, you want the amount you pay to be the expected amount that you should make from this game. So the player has to pay $5 to win the game. So that means that in order for the game to be fair, the amount paid has to be $5 has to be a 12th of the prize money. So the answer is 60. Basically, the idea is that a 12th of 60 is 5.
Yeah, and what I'm doing on the side here is I'm essentially trying to show more of a uh, essentially a visual way to think of these sorts of problems. So and how we can determine probabilities of whether we win or lose. So like,
Foyez, you want more space to write it? I can just go back one slide and then you can just write here.
Sorry. Well, actually, sure. Okay, so odd, even. So essentially what like each of these like nodes represents is really like when we're taking like a move or when we're rolling a die. So is it showing up? There we go. Okay, so if you think about it, so if we have a 1/2 probability to roll odd, but this will always land in a lose. So our winning path is by going to getting an even number, and then getting the same number, right? And so we essentially want to find the probability along this path, right? And so there's a 1/2 probability that I get an even number, and then a 1/6 probability that I get down to the same number. And so that's how you get kind of this like 1/6 or 1/2 times 1/6 probability of winning, and the rest you can calculate in a very similar fashion. So the odd, you have a 1/2 probability of losing, and the even, and then not getting a not same number, you have a 5 times 6 times 1/2, so 5/12 probability of losing, plus the 1/2 already over here. So I hope that makes sense just as a visual diagram.
Yeah, okay, it looks like people are all on the same page here. So I'm just going to clear this annotations, and then we can move on to the next problem. Okay, so here, by the way, the bingo number is 37. So if 37 is on your board, cross that out. All right, so the problem here is to find the number of positive integers with 3 not necessarily distinct digits, A, B, and C, with A cannot be 0 and B is not 0, such that both A, B, C and C, B, A are multiples of 4.
So notice here that A, B, C, so it's not the product of A, B, and C, but it's actually just like A, B, and C actually denotes a number. So like if A is equal to 1, B is equal to 2, and C is equal to 3, ABC denotes 123, and CBA denotes 321.
if you're stuck, a hint would be to think about the divisibility rule for 4. So just remember what that says, and if you don't, it's about the last 2 digits of a number. All right, a fair amount of people are getting in the chat, so I think we can just guess it now. So the first step is definitely to think about what it means to be divisible by 4. So you might know or remember that a number is divisible by 4 only if its last 2 digits are divisible by 4. So for example, if you take 136, you don't have to think about the whole number. Just take the last 2 digits, 36. 36 is divisible by 4. So then you know that 136 is divisible by 4. So now we think about that for any value of b, there are 2 possible values for a and c, because we go into 2 cases depending on whether or not b is even or odd. So if b is even, then a and c have to be either 4 or 8. So for example, if you take b is, let's say 4, and then you stick a 4 or 8 at the end, what you have is 4, 4 or 4, 8, both of which are divisible by 4. And you can kind of check this with yourself, and then there's a similar logic that applies when b is odd. So then a and b have to be either 2 or 6, and they can be switched. So because they can be switched, there are 2 possibilities in each of these 2 cases. So you have 2 times 2 is 4. So this represents the either 4 or 8, and this represents the either 2 or 6. Ways to choose a and c for each b. And then now we think about how many b's we can choose, and that is just 10, because there are 10 digits, 0 through 9. So because there are 10 ways to choose b and 4 ways to choose the a and c that match up with that b, we multiply that and we get our final answer of 40. All right, just gonna stay on this for a couple of seconds to check the chat and Q&A, but it does seem like we're good. All right, so we're gonna move on to problem 4. So I will just read it out. How many 4-digit positive integers have at least 1 digit that is a 2 or a 3? And just update on the bingo. This bingo number is 23. So if you happen to have a 23 on your board, then cross that out. All right. So a fair amount of people are getting the answer. Just to give a hint for what the right direction might be, is so there might be a formal name for this. I always just call it total minus. So oftentimes, if you're trying to find the like, let's say you're considering some set of numbers. So here, the set of numbers is 4-digit positive integers, and you want to find how many of them have a certain property. So in the chat, Austin's helping me out here. Apparently, the term is called complementary counting. So the idea is that instead of finding all the amount of 4-digit positive integers that have at least one digit that's a 2 or 3, we just find the amount of positive integers that don't have a 2 and don't have a 3, and then we can just do the total minus that. So by total, I mean how many 4-digit positive integers are there, and then take that and subtract off how many positive integers have a 2 or 3, and that should leave us with what we want. So with that in mind, we'll just give around another minute, and then we can talk about it. All right, so why don't we go over the solution now? So the beginning part is talking about that complementary counting idea. So it says that since we were asked for the number of positive 4-digit integers with at least 2 or 3 in it, we can actually just find this by taking the total, which is the number of 4-digit integers, and then we subtract the amount of numbers that don't have any 2s or 3s. That's the minus part of the total minus. So first we find the total. How many 4-digit integers are there? So the reason it's 9 times 10 times 10 times 10 is because we have 9 choices for the first digit. You have to be really careful with the first digit a lot of the time. This is just general advice because recall that you cannot start off with a 0. So if you have like 0, 1, 2, 3, that's actually a 3-digit number, not a 4-digit number. So the first digit only has 9 options, and then from there it can be any of the digits. So then we have 10, 10, and 10, and that gives us a total of 9,000. And then we use a very similar strategy to find the number of 4-digit integers without any 2 or 3. So you'll notice that the first number is a 7 because you can't have a 0 as usual, but you also can't have a 2 or 3. So it's the normal 10 digits, except 3 of them don't work. So it's 10 minus 3, which is 7. And then the reason there are 3/8 after that is because you can have any digit except 2 or 3. So then it's 7 times 8 times 8 times 8, which is 3,584. And then when you do the total minus, you do 9,000 minus 3,584, which should give you your final answer of 5,416, which a lot of you put in the chat, and I think some of you are really close. So it's definitely possible that there was some arithmetic error. Yeah. All right. So I'll just wait a few seconds. Okay, so I think we can move on. So problem 5, which is number 15 on the bingo board. So you have star flips a quarter 4 times, and you want to find the probability that the quarter lands heads exactly twice. So this is a pretty classic problem. So if you already know it, that's great. But if not, maybe think about how you can derive it. And if you want to challenge yourself, and if you already know how to do this, maybe you can think about how to generalize this idea.
It looks like we're also halfway through, so perhaps we could take a break until a 5-minute break.
Sure.
Maybe get started promptly at like 2:05.
All right. So we will see you guys at 2:05. Until then, get a glass of water, do what you need to do, think about the problem if you want, and then we'll see you in around 7-ish minutes. Foyez, if you want to put up the prompts.
Okay, so let's start back up again. So let's just go right into the solution. So essentially, we essentially want to find the number of arrangements of the group of letters HHTT. So essentially, we want to find how many different orderings can I get two H's and two tails. And so the answer is actually 6. And the way we do that is perhaps some of you may be familiar with this. Some of you may be familiar with this notation. So we did 4 factorial divided by 2 factorial times 2 factorial, which many of you might recognize as 4 choose 2. But essentially what we're saying is we have 4 spots and we have 4 essentially elements. And so there's 4 factorial ways to essentially order them if each of them were considered distinct. But we have 2 of our elements are the same. So we have 2 heads, and then the other 2 are tails, which are also the same. So we're overcounting by a factor of 2 for each of those. So we divide by 2 factorial times 2 factorial, which is 4. And so for each flip, essentially, the total different combinations is essentially 2 to the 4th, because for the first flip, I can have 2 different outcomes. I can get a heads or a tails, and then I can get in the second flip heads or tails, third flip heads or tails, fourth flip heads or tails. So I'm just multiplying 2 times 2 times 2 times 2. So essentially what I get is that the probability that 2 of the flips are heads is 6 over 2 to the 4th, which is 3/8. So essentially we're looking at something like basically like a part to a whole. So how many of the total combinations, which is 2 to the 4th, is are there 2 heads? So yeah, that's the idea. Akash, do you have anything to
add? No, I think you covered it.
Okay, awesome. So let's move on to the next. So this problem is you can if you guys want, you can count the 31 if you like. And for this problem, it's for the bingo board, it's 3. So it states that a 10-digit arrangement 0, 1, 2, 3, all the way up to 9 is called beautiful if, when read from left to right, 0, 1, 2, 3, and 4 form an increasing sequence, and 5, 6, 7, 8, 9 form a decreasing sequence, and 0 is not the leftmost digit. For example, 9, 8, 0, 7, 1, 2, 3, 6, 5, 4 is a beautiful arrangement. Determine the number of beautiful arrangements. So I hope this makes a lot of sense. So essentially, you just don't want 0 to be your first digit. And you want, if I look at the numbers from left to right, and I identify the digits 1, 2, 3, 0, 1, 2, 3, 4, I'll essentially find an increasing sequence, or I'll find 0 first, then I'll find 1, then I'll find 2, then I'll find 3, and then I'll find 4. And 5, 6, 7, 8, 9 will form a decreasing sequence. So I'll find 9, then I'll find 8, then I'll find 7, 6, 5, 4. Okay, let's go over this problem. So just to start, we know that the arrangement of the digits must be a 9, and so why is this true? It's because that since we want the digits from 5 to 9 to form a decreasing sequence, we need 9 to come before 8, 7, 6, and 5. And since we want the digits 0, 1, 2, 3, 4 to form an increasing sequence, and we know that 0 can't be the first digit, 0 essentially has to come after the first digit. And so you can see that there's no arrangement, there's no number that'll satisfy what we want that doesn't begin with 9. So 9 is the first number. And so we can approach counting the number of beautiful arrangements by counting the number of ways to arrange in kind of like a parallel sense. 5 blue balls and 4, I think that should say red. Yeah, sorry, there's a typo. So 4 red balls, where we'll let the blue balls represent the elements in the set 0, 1, 2, 3, 4, and the red balls will be the elements in the set 5, 6, 7, 8. Just because there's only one way to order the elements in each set. And so we can say that since we have like 9 total slots, we have 9 choose 5 ways to essentially choose the slots for essentially where I want to put in 0, 1, 2, 3, 4. And that's just 126. And so why does this actually work? So 9 choose 5 essentially says, perhaps I should actually explain the choose notation. So choose notation essentially is something we use in something called combination. So the way we deal with orderings in ordering problems, so they're split into 2 things. So it's permutations. So permutations are when order matters. So the order of the elements matter. So for example, if I wanted to figure out how many ways I can order the digits 1, 2, 3, that would essentially be a permutation. So there'd be 6 ways to order those numbers in a line. But suppose I just wanted to, I didn't really care too much about order. And so this is really important when we are dealing with identical elements, or when we're dealing with essentially when we want to choose essentially k objects from n possibilities. So in this set, like if my possibilities are the 9 or sorry, the 10 spaces, or sorry, the 10 spaces where I want to, the 10 spaces where I want to place the digits. And we said the first digit has to be 9. And so now we're left with 9 spaces. And we're essentially looking to choose 4 or 5 spaces such that I can place the numbers. Like, so if I choose 5 spaces, that'll allow me to place 0, 1, 2, 3, and 4 in those spaces. And there's only one way to put those in, just because we want them to be an increasing sequence. And so we call that, we denote that as something called choose notation. So we say something n choose k, which we sometimes write as nck. I'd have to draw, yeah, I'd have to draw the other one. I don't think we can do it by computer, but, and what that is equal to is essentially n factorial divided by k factorial times n minus k factorial. And so I left the space here. So this is how we denote it. And if you notice, n choose k is actually the same thing as, it has the same value as n choose n minus k. And so essentially, how can I give a good example of this? Okay, so let's suppose I'm dealing with the number. I'll give an example of how we use choose notation. So essentially, I suppose we're choosing, I want to choose two numbers in the set 1, 2, 3, 4. So this is not really relevant to this problem, but let's say I want to choose two numbers in the set 1, 2, 3, 4. So essentially, I'm not really worried about whether I pick a 2 first and then a 4, or whether I pick a 4 first, then a 2. We'll consider like that sort of, those sort of reverse arrangements as being the same. And so what we would say is that the answer to this is for, this is not too visible. Okay, so it's for choose 2, and so that's equal to 4 factorial divided by 2 factorial times 2 factorial. And so that's equal to, I believe, 6. Yeah, 6. So, and so that's essentially, and if you want to verify that yourself, essentially try and choose, I can essentially show you how we get there. So hopefully you can believe me. So essentially the ways we can choose it, think about it as choosing like 1 and 2, 1 and 3, 1 and 4, then choosing 2 and 3, 2 and 4, and then finally 3 and 4. So essentially I wouldn't be, if I choose it by like holding one number constant, I can only choose the numbers greater than it, not less than it, because if I did that, I would end up with a repeat. So I can actually just denote all those pairs for you. 1, 2, 1, 3, 1, 4, and 2, 3, 2, 4, and 3, 4. Oh, and notice that I'm choosing two distinct numbers, so not the same. So not with replacement, as we would say. And so that's the whole idea. So if you look back here into this problem, I essentially have, since I said that 9 is my first digit, I now have 9, and I want a 10-digit number, I have 9 spaces to fill with digits. And so I want to find, since my numbers 0, 1, 2, 3, 4 are going to be in this order, I essentially want to choose out of those 9 spaces, I want to choose 5 spaces for those numbers to fit in, 0, 1, 2, 3, 4. And so that's 9 choose 5, which is equal to 126, and that's the answer. And it's important to note that like 0, 1, 2, 3, 4, we can only arrange it in one way. So like if I choose 5 spaces, I won't be able to put 1, 0, 2, 3, 4. I have to put 0, 1, 2, 3, 4 because we want an increasing sequence. And then the last 4 digits have to go in the remaining 4 spaces. And there's only one way to put those in again. So I hope this made sense to most of you. And yeah, so. Yeah. And you'll see choose a lot in high school. Maybe not too much actually, but when you're dealing with, if you guys are interested in looking into it, when you're dealing with like the binomial theorem and something called Pascal's triangle to find coefficients of like some sort of like expansion of a function, this will come into play. And if you'd like to learn more, just like do like a quick Google search on that. So yeah, here are these drawings, and we'll move on. Okay, so this problem states how many positive 5-digit integers are palindromes. And note that the problem for like the number associated with this for bingo is 5. Sorry, I think in the last slide I wrote it. I wrote the choose form wrong. I think I wrote. I'll just rewrite it again. Oh yeah, sorry, I wrote it wrong. Not paying attention. So we say n choose k is equal to n c k is equal to n factorial divided by k factorial divided by n minus k whole factorial. Sorry, I didn't realize I didn't make that clear. So that's just for the previous problem. So sorry about that. Yeah, sorry, in the chat I'm seeing this formula on the top is just from the last problem. I was doing a little bit of I was explaining what choose notation is, and I think I wrote it wrong when typing it. So if you're taking any notes or something, just make sure you correct it to this. great. Let's go over this solution. So a lot of you got it in the chat. The answer is 500. So essentially, we're saying that we want an odd palindrome. So we know the units digit must be odd, so it has to either be 1, 3, 5, 7, or 9. And so essentially, we're kind of looking at something like permutation. So we'll have 5 options for the last digit. So I will just
was what compelled.
So we'll have 5. So we'll have 5 options for the units digit. And notice that the 10,000th digit, so the first digit, must be exactly equal to the units digit because it's a palindrome. Oh, and for those of you who don't know, a palindrome is essentially a number that's essentially when read forward is the same as when read backwards. So that's exactly why we want to have that sort of symmetry. And then so for the tens digit, we have 10 options, 0 through 9. And so in the thousandths digit, we'll only have 1 option because we want that to be the same as the tenth digit. And then the hundredth digit, which is in the middle, really can be anything because it's the censor digit of our number. So essentially, you could say it's like symmetric element is itself. So there'll be 10 possibilities for that as well. And so when we multiply that together, we get 5 times 10 times 10. So that's equal to 500 5-digit odd palindromes. Check the Q&A to make sure good.
Looks like we're all good.
Yeah, okay. Let's move on. Problem 9, the number associated for bingo is 19. And it asks how many 3-digit numbers satisfy the property that the middle digit is the average of the first and the last digit.
All right, looks like some people are putting some answers in the chat, so maybe we can go over the solution now.
Okay, right. So we'll let the digits of our 3-digit number be A, B, and C. And so since the middle, we'll say A is the 100th digit, B is the 10th digit, and C is the units digit. And so we want that the middle digit is the average of the first and the last digit. So we'll let B equal A plus C over 2. And so in order for this to be for B to be an integer, we need A and C to have the same parity. And so essentially what parity is, it's either whether the number is odd or even. So notice that an odd plus an odd is an even number, an even plus an even plus even is an even number, but an odd plus an even number is an odd number, and you can't divide an odd number by 2 and get an integer. So A and C have to have the same parity. So we'll say that if we choose A, there will be 9 possibilities to choose for A between 1 and 9, and then 5 for C. Essentially, we're essentially looking for a number with the same parity. So when we and B will essentially just be chosen. Will just be defined as by our A and C. And so the total number of possibilities we have is 9 times 5 times 1 for B, and that's equal to 45. Let's see if there are any questions.
All right, I think we're good.
Yeah, it looks good. So the next question is associated with the number 29. And asks that when John Stewart walks upstairs, he takes one or two steps at a time, and his stepping sequence is not necessarily regular. So that means he doesn't really have like a strict pattern to it. He may take a step up, 1 step, then 2 again, then 1, then 2, in order to climb up a total of 9 steps. How many ways can John walk up a 14-step stairwell? Okay. I guess let's go over this problem. Okay, great. So we'll let an represent the number of sequences of steps that can be taken up the stairs. And so we'll say A1 is 1 and A2 is 2. And so we'll say that any sequence of length n plus 1 is either composed of a sequence of length n followed by another step, so or a sequence of length n minus 1 followed by 2 steps. And that's because our step sizes are limited to 1 and 2. And so what you can realize is that we have the recursion an plus 1 is equal to an plus an minus 1. And notice that this is exactly the Fibonacci sequence, which we essentially can say is, we're saying that matching them, we'll say that an equals f sub n plus 1, so the n plus 1 Fibonacci number. And so we're essentially looking for A14. And so we get, that corresponds to the 15th Fibonacci number, which you can show is 610. Another way you can do it that's not really presented here is you can do casework and really use this idea of like choose notation. So essentially, we're really restricted by the number of 2's we have. So you can do casework on like how many steps of 2 he takes. So he can take 7 steps of 2, 2 steps of 2, 7 steps of 2, 6 steps of 2, 5 steps of 2, all the way down to 0 steps of 2. And you just essentially have to find where can I fit in all my 1's, right? And so I think that's an interesting way to approach it. So yeah, I'll just make sure there's no questions in the chat. Q&A. Oh, so sorry. So the Fibonacci sequence, many people are asking what the Fibonacci sequence is. So the Fibonacci sequence is essentially just a sequence that's defined by where the first terms are 1, for the first 2 terms are 1, and every term after the first 2 terms are obtained by summing the 2 terms that come before it. Like essentially the first couple Fibonacci numbers are 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so forth. And so this is essentially, we've shown that there's like a direct correlation between essentially how we can find the number of steps, how we can find the number of ways we can take our steps and the Fibonacci sequence. And we're actually joined right now by the faculty advisor of the math team, Mr. Dane Eisenberg. He's been a great help to us for the past, I think this is our second year with him.
Hi, everyone. Thank you for doing this. It's all of them. Good to see you all. Oh, hi, Faris. Good to see you all. This is exciting. They've done all the work. I'm so proud of you. I'm glad you all are enthusiastic about math. I'm going to just watch them teach, but it's awesome. And hi. Okay.
He's not taking enough credit. He does a lot. So this is not possible without him. So, big shout out to him.
Okay, so let's move on to problem 11. Oh, well, the solution is already there. So I guess we won't really give too much time to go over it. Sorry, that might have been a mistake on our part. So problem 11 essentially states that a license plate in a certain state consists of 4 digits, not necessarily distinct, and 2 letters, also not necessarily distinct. These 6 characters may appear in any order, except that the 2 letters must appear next to each other. How many distinct license plates are possible? Okay, and so for the bingo, this problem is associated with the number 22. But let's just get into the solution, since basically we kind of like gave it all away. So the way we choose our 4 digits is we essentially just, we're essentially looking at a permutation in this case, just because the order of the digits matters in a license plate. So we have 10 possible single digits, and so there's 10 to the 4th ways we choose our 4 digits, and we want 2 letters, which are not necessarily distinct. So again, we have 26 squared ways to choose the 2 letters. And now notice that like we can treat our 2 letters as a single unit. And we essentially want to find, like, if we line up our 4 digits, we want to find like essentially where can I place that single unit? So between which numbers can I place that single unit? So I can place it before the first number, after the first number, after the second number, after the third number, after the fourth, and after the fourth number. And so there's 5 different places I can place that single unit, since these 2 letters have to be consecutive. And so there's 5 places where I can place these 2 letters. And so essentially multiplying out to find the number of distinct license plates we have is essentially 5 times 10 to the 4th times 26 squared, which I will not calculate because that is a big number, but this is a perfectly acceptable form. Let's make sure there's no questions in the chat or the Q&A.
The Q&A looks good. I think we can move on.
Yeah. Okay, the solution is here as well. And just for this last problem, if some of you are interested in the exact number, I can just calculate it for you. It's I think 33.8 million. I think so, somewhere close to that. I think that's the exact number. Yeah. Sorry, no, it's 3.38 million. 33.8 million. So, okay, that's the answer to this problem. And sorry, we wrote it out again.
Hey, Foyez, because we're wrapping up, it might be more interesting to go problem 13.
Sure. We'll leave some, we have more problems than this. So the problems that we don't get through today, a lot of you can just like go through for homework. But I think problem 13 is probably one of the most interesting problems we put in. So the number associated with it for bingo is 14. And the problem states that a game uses the deck of n different cards where n is an integer and n is greater than or equal to 6. The number of possible sets of 6 cards that can be drawn from the deck is 6 times the number of possible sets of 3 cards that can be drawn. And we're asking to find n. So this will probably be our last problem. If you guys just want to take some time to solve it by yourself, and then we'll go over it, and then we'll wrap up. And it looks like in the chat we're getting a couple of bingos, so that's good to see.
Well, we actually have 2 types. We have bingo, but then we also have bingo with 10 O's at the end. So emphatic bingos. So someone's asking, what is a set in this problem? So when we have our deck of cards, when they're asking about a set, it really just means picking some amount of them. So you could pick let's say 3 of the cards, and then that would be a set. Or you could pick 2 of the cards, and that would be a set. And the ones that you're interested in are the sets in which you draw 3 cards. So hopefully that just clarifies some vocab.
Perhaps your hint is that order does not matter. So no matter, what order you're going to draw these cards, ultimately, if you're ending up with the same 6 cards, then it's then you can't overcount that. So perhaps that might lead you to the right method of combinatorics to solve this problem.
I would also think back to, the choose notation we talked about and how that might really come into play here.
Right.
And try and probably maybe set up some sort of nice equation that perhaps you can solve.
Gotcha. Maya's here.
Yeah. All right. Our 4th captain is with us now.
Hi, guys.
Yeah, so let's actually just go over this because we only have 5 minutes left. So the solution is we say that essentially the number of ways we can draw 6 cards from the deck is n choose 6. So we talked about this notation of how it was how it would be n factorial divided by n minus 6 factorial times 6 factorial. And so that simplifies to this whole thing here. And the number of ways to choose 3 cards from n possible cards is n choose 3. And we're given that the number of ways to choose 3 cards is 6 times as much. Sorry, was it the other way? Yeah, so the number of ways to choose 6 cards, sorry, is 6 times the number of ways to choose 3 cards, I believe. Sorry. Yeah, so the number of ways to choose 6 cards is 6 times the number of ways to choose 3 cards. And so we could just essentially set up this equation. And when we essentially simplify and cancel out like terms, we can simplify this whole big thing here into a simple equation, n minus 3 times n minus 4 times n minus 5 is equal to 720. And so we can think about it, essentially what this is saying is that we want 3 consecutive integers that multiply to 720. So, but how can we find these 3 integers? A good way to think about this would be, again, to prime factorize and see if you can find if you can create 3 numbers that are somewhat close together. And so a clever hint here is since 720 is close to 729, which is represented as 9 cubed, we could try 8, 9, and 10. So that's a really good idea to think about. And it actually works. So like 8 times 9 is 72, times 10 is 720. And so now we just have to essentially find n. So our biggest number is n minus 3. And so that's our biggest number here is 10. So we'll set n minus 3 equal to 10, and we'll get n equals 13. And so yeah, that's the answer to this problem. So I hope this whole session was really good for you guys, and you learned a lot, at least, and got some good practice with competition problems. There are, I believe, 3 problems that we didn't go over: question 12, question 14, question 15, and I think perhaps there is a question 15, 16. So there's actually 4 problems, and you guys could finish that for homework, and we can definitely go over those tomorrow at the beginning of class. Yeah, I mean, I hope you guys really enjoyed it. Anything else from you guys?
No, I think that's it, logistics-wise. Of course, we'll see you all tomorrow at the same time. Yeah, so just thank you. Be on the lookout for an email with the slides and homework. And oh, and Michael, I just want to note out that Michael also put in the link to our YouTube. So of course, feel free to watch the recording of this later if you want to go over anything when doing the homework or at a later time. Yeah, so feel free to watch that or click through the slides.
Yeah, and homework will be attaching this presentation to our website. So if you just want to check it out there, the homework will be attached to this as well. So yeah, thank you guys for tuning in.
Thank you.
Everyone.
All right, see you tomorrow.